Hi there, I'm Borna, your organic chemistry tutor, and I'm back with another work mechanism problem that is going to challenge you. Let's get started. Alright, so today I have this mechanism problem for you. You should be able to try this if you have learned conjugate addition. So pause the video, go ahead and try this mechanism and come back. Alright, so looking at the starting material, what I notice is that I have an alpha beta unsaturated carbonyl compound. Okay, so I have that right there. And I have an aldehyde, and I have basically a product that has more rings than I started off with. So that to me suggests that probably one of these carbonyls, and I'm suspecting probably this, got enolized since the double bond is no longer existent, probably did a Michael addition with the alpha beta unsaturated compound, and probably an aldol condensation. But you know what? I'm not going to get ahead of myself. I'm going to go ahead and number the carbons of the starting material and see if I can find them in the product. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And it's very unlikely that the methyl on carbon 7 gets displaced. So I'm going to number this 7. And from there, it actually makes sense that this would be 9. This would be, that would be 8. This would be 9. And then I'd have 10 here. 10 is connected by 11 and 6 to 7. So I'm going to go 11 and 6 right here. And 6 and 7 are connected together. Or basically 6 and 7 are connected together by a bond in the starting material, but 6 is connected to 5, 4, 3, 2, and 1. Alright, now 6 is connected to 5, 4, 3, 2, and 1. Alright, now as for the bonds that are being broken and the bonds that are being made, so broken are going to be red, made are going to be green. Obviously, the bond between 2 and 7 did not exist. That bond is being made. The bond between 1 and 10 did not exist. That is being made. The carbon-oxygen double bond, the double bond of it, and 1 is being broken. And the double bond portion of the bond between 7 and 9 is being broken. Now, let's analyze that. 2 is an enolizable position adjacent to an aldehyde. If I analyze that, that is actually a sensible thing to do, so that makes sense. Let me just go ahead and use my base to enolize this position. That is going to create an enolate right there. And that creating an enolate means that it's a very good nucleophile, and it'd have a tendency to attack 7, and that's probably how 2 and 7 get connected. So I'm going to go ahead and do that and see where that takes us. So I have this, I'm going to do this, and this is going to lead to another enolate, which I'm going to draw using my numbering as a guide. So I have 4, 5, 6, 7 like this. I'm going to create a 1, 2, 3, 4, 5, 6. Oh, actually, rather, sorry. 1, 2. 2 is getting connected to 7. So I'm making a 1, 2, 3, 4, 5, 6 member drink in addition to what I have. So I'm going to draw that. So I'm going to have a enolate right here. I'm going to have my carbon 2 connected to carbon 7 being right here, and 6 being right here, and then 2 is going to be right there. 2 is going to have an aldehyde coming off of it, and then 3, 4, and 5 are going to be right here. Now, if this thing abstracts the hydrogen from water, that basically can become a neutral dicarbonyl compound. And I'm going to draw that in a slightly more suggestive functional group that'd help us see how carbon 3 gets connected, or rather, sorry, carbon 10 gets connected to carbon 1. So see, carbon 10 has to get connected to carbon 1. Carbon 10 is right here, and carbon 1 is right here. Now, carbon 10 can get enolized, and well, that enolized carbon can very easily attack that aldehyde, open it up in a nucleophile electrophile fashion, and basically this pretty much looks like what I have in the product minus that bond that I have. So let me go ahead and paste the numbering here. So I have 7, 6 there, I have 8, 9, 10, and I have my carbon 11 right there. So I'm gonna draw a 6-membered ring just like I have in the product. I'm gonna try to make the structure of the intermediate that I have like that of the product. So in the product I have 9 here, I'm gonna place 9 there. I have 9 here, 10 here, 11 here, and then I have 8 here, 7 here, and a 6-membered ring basically connecting 6 and 7. So I'm going to have 6 here, and then I'm going to have 2, 3, 4, and 5 here, and there's going to be an aldehyde coming off of 2, which is going to be my carbon 1. Now I'm going to make this look a little neater. Just bear with me for a second. Now I'm gonna... Alright, now this looks pretty similar to the product to me. All that needs to happen is that carbon 1 needs to get connected to carbon 10, and that is not that difficult. If I have my base basically abstract a hydrogen right here, that is going to create an enolate. For ease of drawing, I'm going to copy and paste the structure. Sorry, I'm being lazy with that. And then basically this is going to give me an enolate just like this. And this enolate can attack this aldehyde that I have right here, open this carbon-oxygen double bond, and that is going to lead to a structure that is basically 1 proton transfer away from my product. Okay, I'm going to draw this a little further down, give myself some space. I'm going to have a carbon-oxygen double bond right here. I'm going to have my methyl right there. I'm going to have an O- right here. If I'm missing anything, I don't believe so. And then this can just abstract a hydrogen from water, and this is going to give me a product. And I'm going to have to go through the fun process of trying to draw this molecule again. But regardless, there you have it. This is the product.
Well, I hope you benefited from this video. If you did, please consider hitting the like button. That's going to help my channel grow. Also, please subscribe to see more tips and tricks, tutorials, and solved problems. I regularly upload videos. I'll see you in the next video, and take care.